All right, this is problem set 38. We get to introduce Gibbs free energy. So we've been talking about enthalpy, which is heat. That tells us if something is exothermic or endothermic. Excuse me. Then we talked about entropy. So this is enthalpy. We talked about entropy, which is disorder or dispersion of energy. Okay, and we talked about how delta S, the universe, has to be greater than 0 for something to be spontaneous. Okay, the universe. Now our goal here is to figure out when something's going to happen or not. If we know the delta S of the universe, then we know if something's going to happen or not. The problem is it's really hard to measure the universe. We know that the universe is the system and the surroundings, okay? But the system's rather easy to measure, but in a lot of cases the surroundings is not. And so basically what we want to do is we want to come up with a term that is only in terms of the system to figure out if something is going to happen or if it is not. Okay, so let's do that. We know that delta S of the universe equals delta S of the system plus delta S of the surroundings. And I'm actually going to rearrange it, delta S of the surroundings plus delta S of the system. Okay, so we're going to make one change here. We talked in problem set 37 about how when we're talking about the surroundings being like the whole world, okay, when we add heat to it, the temperature doesn't change, and so we can calculate the delta S of the surroundings as the heat going into the surroundings divided by T. Q reversible over T. You can also write that as delta H surroundings over T surroundings. Okay, but again, we want things in terms of the system. But if you remember, the first law of thermodynamics says that the change in energy of the universe has to equal 0. In other words, delta H of the surroundings and delta H of the system have to be, remember, no subscript means system, have to be equal and opposite. If something leaves the system, it must enter the surroundings. If something leaves the surroundings, it must enter the system. So I can replace this delta H of the surroundings with negative delta H of the system, and I'm just going to write T. T of the surroundings isn't that big of a deal because that's usually what we measure, right? It's easier to measure T of the surroundings in the system. So in other words, delta S of the surroundings is equal to negative delta H of the system over T. So I'm going to plug that in. Delta S of the universe is negative delta H of the system over T plus delta S of the system. And again, I'm going to leave no subscript because that means system. Now what I'm going to do is I'm going to multiply every term by negative T because I'm going to get rid of this. And that leaves me with negative T delta S of the universe equals delta H minus T times delta S of the system. And some guy named Gibbs comes along and he names this delta G. And we call this delta G Gibbs free energy. Let's talk about what that means. Basically, our process, things are trying to get to a low energy state. Okay, but it's not a low enthalpy state. It's going to be a low Gibbs free energy state. Let's talk about what that means. When a process happens, it has some enthalpy involved. Okay. And that enthalpy, if it's releasing heat, that heat can be used for stuff. Okay. But unfortunately, it can't be used, not all of it can be used, because in any process, some of the energy is lost to entropy. So that energy that we get from a process, that enthalpy we get from a process, we need to subtract out this term involving the entropy, because entropy is always increasing. So we're always going to lose something to entropy. And whatever's left, that's the amount of Gibbs energy or free energy, available energy, that we have to do stuff with. So if that didn't make sense, let me give you another example. Let's say that you have a $100 gift card to a brick and mortar store. Does that mean that you can buy $100 worth of stuff? The answer is no. Why? What always gets taken out when you buy stuff? taxes. Or another way to put that is you're always spending money on taxes, and so the actual value in terms of what you can buy is going to be something smaller, let's say 93. Does that make sense? So we have a certain amount of enthalpy from our process that we get out of our process. We lose some of that to taxes. You could also call this shipping if it's an online store, right? And so our actual amount of energy or amount of money that we can do stuff with is less than what you would predict because of the effects of entropy. We call this the free energy. Free meaning available. Now let's look. We see right here that delta G equals negative T delta S of the universe. Well, we said that if delta S of the universe is positive, that process is spontaneous. Because temperature is always positive, that means if we want that to be positive, G would be negative. So G is negative for a spontaneous process. So I can write this. Non-spontaneous, delta S of the universe is negative, which would make delta G positive. Okay, so the sign flips just because of the way that we defined it. This really helps us to see the way that temperature affects a process. So I'm going to have delta G equals delta H minus T delta S. Make a little table here. Let's say that I have something that is endothermic. Delta H is positive. And the entropy increases. How do I want to do this? Let's do this. Delta H, delta S. There we go. And then I'll, okay, sorry I'm rearranging this so much. We're going to do this. Okay, so let's say we have kind of 4 scenarios. We're going to see when each of these scenarios produces a spontaneous process. And we'll be able to see how temperature affects this. So, and again, our equation is delta G equals delta H minus T delta S. All right, so let's say delta H is positive and delta S is positive. If temperature was 0, this whole term would go away and delta G would be positive. So we know at very low temperatures, like temperature 0, this is not spontaneous because delta G is positive. But what happens when temperature starts getting bigger? All of a sudden this term starts to matter, and I'm subtracting a positive value. So this value is going to get lower and lower and lower until eventually, so let's say T was infinity, and I would have a positive value minus an infinitely big value, and G would then be negative. So this is spontaneous at high temperatures. What about if delta H was positive and delta S was negative? Well, then I have a positive value, and I'm subtracting a negative, so I'm adding something to it. So it doesn't matter what the temperature is, I'm always going to have positive plus something. So this is always not non-spontaneous. All right, what if I had negative and a positive? Well, then I have a negative value, and I'm subtracting a positive value. So that's negative, and no matter what the temperature is, it's always going to be negative. So this is, so I should say this is never spontaneous. This is always spontaneous. And lastly, what if I had negative and negative? Then I've got this negative value, and I'm adding something to it. So at low temperatures, what I add will be very small. So at low temperatures, I'm going to be negative. My delta G will be negative. But as T gets bigger, the number I'm adding gets bigger, and eventually delta G will become positive. So this is always spontaneous at low temperatures. Okay. So we've introduced you to the delta G equation and conceptually what delta G is. So let's take a look at here. Gibbs free energy. Define it. The book and the world likes to say it's energy available to do work. Just like in my gift card analogy, it's the money available to buy stuff, to actually do something with. Gibbs free energy is the energy that you can actually do stuff with. What does the sign of delta G tell you about spontaneity? Negative delta G is spontaneous. In other words, that process goes from high energy to low energy. All right, what does it mean for delta G to equal 0? Okay, this is an interesting idea. So we know that if delta G is negative, something's going to happen. It's spontaneous. If delta G is positive, then that process is non-spontaneous. Another way to say that a process is non-spontaneous is to say that the reverse process is spontaneous. So for example, in my freezer, it is not spontaneous for ice to melt, which means it is spontaneous for water to freeze. Okay? When delta G is equal to 0, we call that being at equilibrium. In other words, the process isn't going forward and it's not going backwards, it's just sitting right at whatever stage it's at. Okay. Describe 2 ways that delta G can be calculated. So we did talk about delta G equals delta H minus T delta S. So if you can get the delta H value and the delta S value, and you know the temperature it's happening, you can get your delta G. Okay, that will give you the delta G for any temperature you want. If you just want the standard delta G, which means at 25 degrees Celsius in 1 atmosphere, then you can just look up the delta G of formation values, and again, do products minus reactants. That's how do I do this? N times delta G naught of formation products minus N times delta G naught of formation reactants. Okay, very similar to delta H's of formation. Okay, the figure at the right is a plot of Gibbs free energy. So this is G. Keep in mind it's not delta G, it's just G as a function of a chemical reaction. Pure reactants on the left, pure products on the right. 3 points appear on the plot. For each point, answer the following questions. What is the sign of delta G? So let's just do it. So at this point, what's the sign of delta G? Well, delta G, if this is G on the left, delta G is the slope of this line. Right there. So here, delta G is negative, which means it's spontaneous. Justify each of your answers. Okay, so what that means is that if I have this combination of reactants and products, let's just say I have a beaker and I have some product or some process, and I dump in, like, this is like mostly reactants and not many products, the reaction is going to go forward. It's going to move that direction because it'll be spontaneous at that combination of reactants and products. What about this one, though? At this combination of reactants and products, okay, delta G is positive. So it's going up, delta G is positive. And as a result, this is non-spontaneous, which means instead of the reaction going forward, the reaction is going to go backward and move to this point, at which point delta G is equal to 0, which means we're at equilibrium. Which means the reaction is going to move, and it's going to get to this point, and it's going to stop moving. This brings up an interesting and important idea of equilibrium. We, for most of the class, have treated reactions as if they go from 100% reactants to 100% products, and that's really not how things work most of the time. Usually if you have a reaction, you put in your reactants, they react, and at some point, at some ratio of products to reactants, they stop. They've reached equilibrium, and it's no longer thermodynamically favorable to go all the way to completion. And so we have this equilibrium point. So again, to the left of the equilibrium point, we're moving forward towards it. If we were to go past, then it becomes non-spontaneous, and we would go the other direction to get to equilibrium. All right, what's the sign of delta G for the following process? Remember, spontaneous reactions occur without being driven by an external source of energy. Remember, delta G tells us if something is going to happen or not. Okay, so negative delta G is spontaneous. Positive delta G, not spontaneous. Okay, and this just means it happens in real life in whatever conditions are given, and in this it doesn't happen. Okay, so wood burns in air after being ignited. Does that happen? Yes. Negative delta G. Water vapor condenses on the side of a glass of root beer. I know that happens as long as root beer is cold, right? So that's going to happen, so that's going to be negative. A broken cell phone is repaired. If my cell phone is broken, does it just spontaneously or on its own be fixed? Nope. So that's non-spontaneous, so it's positive. Remember, this is delta G. Salt dissolves in water. That happens. That's negative. Photosynthesis. Does photosynthesis happen? Sure it does. So that's negative. Okay, now, at some point, people might argue with that and say, no, photosynthesis isn't spontaneous because you have to add energy all the time. Well, it depends on your conditions that you define. If I've got a flower sitting in the sun and that flower's alive, it's going to photosynthesize. So in that set of conditions, if this is my universe, which to me, this is the universe, right? Then photosynthesis happens, so it must be spontaneous. A hot soup gets cold. Okay, that's true, unless, of course, it's sitting on the stove. But I think the assumption here is that you've just got hot soup on the table. It's going to get cold. Muffins rising in the oven. Well, that kind of depends. I think the assumption here is the oven is on. And under those conditions, that definitely happens. So that's going to be negative. And lastly, you get an A in this course. That's kind of a jokey one, but the idea here is that if you were to just stop and do nothing from here on out, you would not get an A in the class. But some of you will get A's in the class, and therefore for you, on the condition being you're the person, you could say it's spontaneous. Again, it doesn't really matter, kind of a joke one. All right, what are the signs of delta S, delta H, and delta G for the formation of dew on a cold night? Let's talk about what each of these tell us. Delta S says if things are getting ordered or not. Let's say, I'm going to say disordered. Delta H tells us if things are endothermic or exothermic. And delta G tells us if things are spontaneous. So these are really the questions we're asking. Dew forms on a cold night. It's going from vapor to liquid. Is that getting more or less ordered? More ordered, so delta S must be negative. Okay, is dew forming exothermic or endothermic? We've got a vapor going down to a liquid. That's going to release energy. So that's exothermic, so delta H is negative. And G, does dew form on a cold night? Sure it does. So delta G is also negative because it's spontaneous. Okay, sublimation of dry ice at 25 degrees Celsius. Okay, if you've ever seen dry ice, it looks like it's smoking. That's just carbon dioxide going from solid to vapor. Is that becoming more or less disordered? That's more disordered, going to a vapor from a solid. And that requires energy. Energy has to go in to make something sublimate. So delta H must be positive. And we ask ourselves, does that actually happen? Sure it does. So delta G, if it hadn't happened, you would never have seen it happen, right? So delta G, and specifically it happens at 25 degrees Celsius, which is kind of normal conditions. Delta G must be negative. And making ice cubes in the freezer. And going from liquid to solid, that's going to become more ordered. So delta S must be negative. And when it goes from liquid to solid, it's going to release heat. So delta H is negative, and that does happen. So delta G must also be negative. Okay. On the right is a plot of delta H and T delta S for a phase change as a function of temperature. So we've got temperature on the bottom. Oh, come on, pen. There we go. Don't know what happened there. We got temperature on the bottom. We have a value for T delta S and a value for delta H. Okay, remember, delta G equals delta H minus T delta S. So what is the status of the process at the point where the two lines intersect? Right here. What that means is that delta H equals T delta S. So delta H minus T delta S would mean delta G is equal to 0. So that point is equilibrium. And it's a phase change, so that must be like the temperature of the phase change. Like that's 60 degrees is the temperature of the phase change, because that's the point at which it's equilibrium. It could go either way. Okay. Over what temperature range is this process spontaneous? So over what temperature range is delta G less than 0. Well, delta G is less than 0 if T delta S is bigger than delta H, because we're subtracting T delta S from delta H. So over here, I guess I could do this. This range, right? T delta S is above delta H. So in this range of temperature being less than 60 degrees Celsius must be spontaneous, because T delta S is bigger than delta H. And lastly, of the 6 phase changes, melting, vaporization, condensation, freezing, sublimation, and deposition, which ones have thermodynamic profiles that fit this pattern? Kind of a confusing question, but basically this is saying this process is spontaneous at low temperatures and not spontaneous at high temperatures. Which other processes, phase changes, are spontaneous at low temperatures and not high temperatures? Melting happens when you increase the temperature, so that's not one of them. Vaporization happens when you increase the temperature. Condensation happens when you decrease the temperature. Freezing does as well. Sublimation happens when you increase. Deposition happens when you decrease. All right, so that's delta G, kind of a conceptual introduction. Hopefully that helps. Problem set 39, we're going to be doing applications, and that's when really the math is going to come into play.